Hello students, in this lecture we will see some examples based on monotone sequences. Monotone sequence is the sequence which is either non-increasing or decreasing. When Sn is less than or equal to Sn plus 1, then for all n belongs to I, then we say that it is non-decreasing. And when Sn is greater than or equal to Sn plus 1 for all n belongs to I, then we say that it is non-increasing. Let us see this example. We are going to solve these two examples in this lecture. So this first example, you have given that these both sequences are non-decreasing as well as bounded. Also, one relation we have given that Sn is less than or equal to Tn, and we have to prove that limit of Sn is less than or equal to limit of Tn. And in this, we have to find limit of this sequence. So let us solve this question. So what is given here? First we will write given Sn and Tn. These sequences are non-decreasing and bounded. So here, two things we can say. As the sequence is bounded, there exists greatest lower bound as well as least upper bound. So for both of the sequence, there exists GLB as well as LUB. Now, as the sequence is not decreasing, as per the theorem that every non-decreasing sequence which is bounded above is convergent and converges to its least upper bound. So here we can say that these two sequences Sn and Tn are convergent and both converges to its least upper bound. So let us write down. So this implies there exists M for this sequence Sn and T for this sequence T. Greater than 0 such that Sn is less than or equal to M for all n belongs to I, where this M is LUB of this sequence Sn. And for Tn, there exists this T such that Tn is less than or equal to T for all n belongs to I, where this T is LUB of the sequence Tn. So as both sequences are convergent here, we can say, because these are not decreasing as well as bounded here, limit of Sn is M as M is LUB. Similarly, limit of Tn is T as T is LUB of the sequence. Okay. So also we have given one more relation. Consider this. Consider Sn is less than or equal to Tn, and it is given for all n belongs to I. Now, Sn is less than or equal to Tn, but Tn is less than or equal to T, isn't it? For all n belongs to I. So it means that Sn is less than or equal to T for all n belongs to I. So what it means that T is one of the upper bounds of the sequence Sn. So we will write it here. We want to show that limit of Sn is less than or equal to limit of Tn here. This implies that T is one of the upper bound for sequence Sn. So taking limit of both sides, let us give number 1 to this. So 1 implies limit of Sn as n tends to infinity is less than or equal to t. But what is limit of Sn? Limit of Sn is n. Why? Because this Sn is convergent sequence and it converges to its least upper bound. Right? So what we are getting? So in the next part we will see this example. So this implies limit of Sn as n tends to infinity is less than or equal to limit of Tn as n tends to infinity. Hence the proof. Well, why we can say that this? Because n is the least upper bound and therefore limit of Sn is n. Same for this one. You can write it here. Since Sn and Tn are convergent sequences. Why these are convergent? Because these are non-decreasing as well as bounded. This implies limit of Sn equal to m and limit of Tn equal to t as n tends to infinity. Yes. So let us solve another example. Question 4. So in question 4, we have to find the limit of the sequence. So let us consider that sequence. Question 4. So we have to find limit of the sequence. So consider here Sn is n raised to minus n minus 1 into n plus 1 raised to n. So as only we have to find limit, we will consider directly the limit. Consider limit of Sn. Limit n raised to minus n minus 1 as n tends to infinity. So let us first simplify the term and then we will evaluate. So we can split it now n raised to minus n into n raised to minus 1 and this is as it is. Now this n raised to minus n can be written as 1 upon n raised to n. So this is limit as n tends to infinity 1 upon n raised to n, this term, into, again this n inverse can be written as 1 upon n and n plus 1 raised to n. Now, this n plus 1 raised to n, I will combine with this denominator n raised to n, so that I can write n plus 1 upon n whole bracket raised to n. And this 1 upon n, we will write it other side. So, this is limit as n tends to infinity 1 upon n, we have written it here, and then n plus 1 raised to n upon n raised to n. Now we can write it in one bracket. So here we will get it as this is limit as n tends to infinity 1 upon n, and this can be written as whole bracket raised to n. And now in this term, we can divide by n into, now this can be written as, yes. So now we can split it. So limit of n tends to infinity 1 upon n into limit of this bracket. So So this is equal to 0 because as n tends to infinity, 1 upon n tends to 0 into, now we have seen in the last lecture that this limit is e. We have also proved. So for this you can see that this is equal to 0. So finally, what is limit of the sequence Sn here? If nth term is given as n raised to n minus 1, then limit into n plus 1 raised to n, then limit is 0. So thus we got here the limit of the sequence.